Our next lesson, and the last lesson before the mid-module assessment, is lesson 16, which talks about between figure and within figure ratios. So again, we're using ratios between similar triangles and answering questions about angles or side lengths. And in this lesson, we talk about different kinds of ratios that you can use to answer these questions. This lesson covers two CCRSM standards. The first we've seen before, where we're using similarity to solve problems and prove relationships in geometric figures. The second one is to use geometric shapes and their measures and their properties to describe objects. So answering mathematical questions about things we interact with in the physical world, like tree trunks and human torsos and other things that are geometric in shape, but aren't really just geometry shapes. Anyway, let's get started. Lesson 16 starts off with this problem, which has to do with shadow length. Now, it's hard for us to measure with like a measuring tape the heights of trees and the heights of buildings and the heights of very tall things. And so we found other ways to measure the heights of them, and one of those ways is by using shadows. It's not the most common way, but we can use shadows to measure the heights of trees. And how this works is that at any time of the day, the angle of the shadow being cast by a building or a tree or a flagpole or something else, they're all at the exact same angle because that's the angle that the sun is away from those objects. So here I have a tree that's casting a shadow that's down here, and a flagpole which is also casting a shadow. Now, these don't have to be, right next to each other at the perfect angle, but for the picture, we're drawing them this way. Now, before I do anything else, I want to first ask the question, are these triangles similar? And there are three ways that we can talk about triangles being similar. We have the angle, the side angle side, and the side side similarity criteria. Now, we are assuming that we want to measure the vertical height of this tree. Even if it was leaning, we want to find the vertical height of this, and so the height will be perpendicular to the base. Similarly, the flagpole, almost every flagpole I've ever seen, is perpendicular to the ground. And so that's one of the angles. And the other part is this angle, or the angle that's made by the sun. And so both of those triangles, the little one with the flag and the big one with the tree, by angle, they must be similar. And because they're similar, then these ratios must hold. Now, the question that we are asked is to write an equation that would allow you to find the height h of the tree that uses the length s of the tree's shadow. Now, there are two different kinds of ratios you can use to answer this or almost any question about similarity. One method is by using the between figure ratios. Now, I commonly call this corresponding ratios because they have to do with corresponding sides. So between figure ratios is where you would compare 8 meters and the length s. Now, this is a small triangle to big triangle ratio, and that would be equal to 12 to h, because those are also corresponding sides, and they're also small triangle to big triangle equals small triangle to big triangle. Okay, that's one proportion we could set up to answer the question. The other ratio we could use is the within figure ratios. This is where you look within the figure to find some ratios. So I'm going to compare the height of the flagpole to the shadow of the flagpole within that same figure. So I'm looking at 12 over 8 is equal to the corresponding height of the tree to the shadow of the tree, h over s. Okay, so I'm using each of those ratios are within the figure as compared to being between the two different figures. Okay, now you can use either method to answer this question. I'll finish this problem using either method to show you. But the point of the problem that I want to point out is that you can use either between figure ratios or within figure ratios. Now, to answer the question of writing an equation that solves for h, where we can find the height of the tree using s, the length of the tree's shadow. So I will cross multiply. And then to solve for h, I must divide both sides by 8. And h is equal to 3/2 s. Now, solving this proportion, I get the exact same thing. All right, let's look at this question, which is not in a real-life context, but I can show you using geometry shapes the exact same ideas. Now we can look at either between figure ratios or within figure ratios, and many students, and probably you as well, your brain will naturally find the ones that are the easiest. Okay, so for example, with a between figure ratio, you might say, oh, hey, look, 4 and 12, they correspond with each other, and 4 times 3 is 12, using a scale factor. So that must mean if I take 5 and times 3, I get 15. Okay, that's using a between figures ratio to find the length of a prime b prime. Now you also might notice that, hey, look, if I look at this within ratio, that this length 6 is half of 12. And so I can look over here and look at this within ratio and say this length must be half of 4, so this length must be 2. Okay, now the point is that you can use either between figure ratios or within figure ratios. Many students will kind of just look at it and their brain will find out the easiest solution, easiest way to find that solution. But you can use either way, either by using kind of this scale factor method or by setting up a proportion. Now the last problem in this video is example 2, which looks very similar to me to the tree and flagpole problem. Here's a building and flagpole problem, but it starts off by saying, in the diagram above, a large flagpole stands outside of an office building. Marquise realizes that when he looks up from the ground 60 meters away from the flagpole, the top of the flagpole and the top of the building line up. If the flagpole is 35 meters tall and Marquise is 170 meters from the building, how tall is the building? So here we're given the distance away from the building, which we can measure on the ground. And the question is asked, are the triangles similar? Well, the answer is yes, for the exact same reason as we mentioned before with the flagpole, that the flagpole is perpendicular to the ground, and so is the building, or at least it's measured in height perpendicular from the ground. And if Marquise is standing, so it lines up with the top of the building, then this angle will be the same for both triangles. In letter B, we're asked to determine the height of the building using what you know about scale factors. Now, if I think about this as a dilation, where this is the center of dilation, I'm dilating the height of the flagpole onto the building, and think about that as similar triangles, then I can find the scale factor by dividing the image length divided by the corresponding pre-image length as 170 over 60, which is 2.83 repeating. That's the scale factor between the triangle with the flagpole and the triangle with the building. Now I can find the height as the scale factor, 2.83 repeating, times the height of the flagpole, 35 meters, and that is equal to 99.16 repeating meters. That's using scale factors. Parts C and D asks us to solve the exact same question using the between figure ratios in C and the within figure ratios for D. Now, in C, you're looking at the corresponding or the ratios in between the figures. And so I'm looking at 60 over 170. is equal to the corresponding length, the small to big ratio, which is equal to 35 over h. All right, now you solve this by cross multiplying. And again, we get 99.16 repeating meters. Now the last method is by using the within similar ratios, where I'm looking at the height of the flagpole divided by the shadow length, for example, and that's equal to the height of the building divided by the length of the shadow of the building. And again, this is a height to shadow ratio for both of them. And then once I have the proportion, I solve it. And again, I get 99.16 repeating meters. Now, the point of this question to me is not what is the height of the building, but being able to do this in multiple ways. I'm hoping that you can see how to use between figure ratios and within figure ratios, and that you can use either one to solve problems. This video was about using between figure ratios and within figure ratios to solve problems with similar triangles. Thanks for watching.